I'm in one of those funny mood today, so you're just gonna have to get used to me. But that's cool. So, where are we? Oh, we are working on a new section, and 12.4 it is, and it's the cross product. And we did the intro yesterday, so I won't go into that again. But essentially, if you have two vectors called A and B, and what you're trying to do is you're trying to find a third vector that's perpendicular to them. And it's called the cross product. And there is a formula that you've not seen because I don't write it down, but if you want to, I'm sure you can find it in the textbook somewhere for calculating the cross product. Essentially, the best way to do it is like this. It's a process, right? It's a thing that you do rather than a formula that you use. So you set up a 3x3 matrix, and the first row is always going to be called I, J, and K. The second row is going to be your first vector, this one, and you write down 5, -2, and 1. And the other guy you write down is 3, 0, and 2. So that's the first stage of the process, is you set up this little 3x3 matrix, and you find what's called its determinant. And the answer to the cross product is so many i's, take away so many j's, plus so many k's. So the number that goes here, the number of i's, you cover up the column that's got an I in it, and there's a little 2x2 matrix left. And essentially what you do is major diagonal, take away minor. So -4 take away nothing is -4. If you want to get the j component, the number that goes here, cover up the j column, and you've got a 4x4 matrix, right? And its discriminant is major diagonal 10, take away minor diagonal 3, 10 take away 3 is 7. And if you want to get the k component, cover up the k column, and 0 goes this way, right? So major diagonal nothing, take away -6 gets you 6. And then you finish with -4. The negative of this guy is -7, and this guy is 6. And there is your cross product. I'm not making any explanation of why you would want to calculate a cross product, but you'll be surprised later on its uses. The things that it actually tells you are quite interesting. Now, if I had time, actually, since it's the beginning of today, I will do it. I can prove, or at least check, right, that this guy is actually perpendicular to those two, right, orthogonal. If you do a dot product, that's A, which is 5, -2, 1. Dot product with this guy, 4, -7, 6. Provided I haven't screwed up my calculation, shouldn't this be 0? Because they're orthogonal. See what they are. 5 times -4 plus -2 times -7 plus 1 times 6. And that's -20 plus 14 plus 6. Am I good or am I good? I did it right. So you could use that, couldn't you, to check that your dot product, to check that your cross product is in fact right. Easy in WebAssign, it just tells you you're right. But if you're doing a test, that's how you would do it. Now, I don't really want to do the other one, but if I did the cross, this guy with this guy, I would also get 0. Any questions about that process? How to find cross products? Okay. Let's suppose I have a cross product of these two vectors. So I'm just using this as another practice example. So I write down I giant K. I write down A. I write down B. And then it's so many I's. That's always going to be take away so many J's plus so many K's. And you just do what we did before. You want to get the guy that goes here, the I's, cover up the column, major diagonal, nothing, take away -3, gets you 3. You want the middle one, nothing, take away -2, gets you 2. Cover up the last one, you get 3, take away 2, leaves you with 1. The cross product would be 3, -2, and 1. I hope by now that you're beginning to feel comfortable with this. It's quite a mechanical process, right? You just kind of do it every time the same way and you're going to get the answer. So you're going to make me feel happy because I'm going to give you 2 vectors and you're going to find the cross product. And if you can do this one right, then I'll be happy to just move on to the next piece, cross product stuff. So no particular numbers, I'm just picking things that come into my head when they come into my head. There you go. You should be able to do that in 2 minutes. So no pressure, 2 minutes starting now. Okay. I'll take any volunteer. Anybody feel up for the challenge of getting the answer to this?
5, -3, -7.
Okay. So you said 5 here. Let's check it. Major 4, take away negative. Nailed that one. Your middle one would be 1, take away -2, which is 3. And your last one was 1, take away 8, which is -7. I definitely remember you saying 5. And I'm assuming the other 2 were right. Okay. Basically, shouldn't you be able to find the cross product of any 2 vectors now? Isn't the only thing going to change is the numbers. So that's a good thing to be able to do. I'm happy with that. Let's move on and look at cross products. Of I, J, and K. In case you need to be reminded, I is 1 in the X direction, J is 1 in the Y direction, and K is 1 in the Z direction. And you can find cross products of any 2 of those in any order. I cross J ends up being K. Does that make sense? That if you go 1 in the X and 1 in the Y, what vector is perpendicular to the X and Y axis? Would you agree it would be the Z axis? That seems reasonable. What might not be obvious is what happens if you switch the places. Now, since I've not done this yet, you're really guessing or you're being intuitive, but what do you think might happen if you did the same calculation but switched these round?
Would it be -K?
Interesting. Yes. Any ideas why you were thinking that?
I was just like thinking of, the axes, if you have like going one direction and then, I don't know, you just like twist it and then it's going the other way. Real succinct description there.
It is. There's a thing called the right hand rule, and there's another one called the left hand rule, where you do your index finger, your thumb, and whatever that finger's called. And this is my left hand that I'm using right now. And the direction of your thumb is the cross product. So if this is A and this is B, that's A cross B. And that's called the left hand rule. And when you do it with this one, it's called your right hand rule. And there we go. We use the right hand rule. X axis, Y axis, Z axis. I can't straighten my fingers that way, but can you trust me? Evidently, people who do electrics and force fields are forever using left hand rules and right hand rules because it tells them something to do with the direction of the flux or the magnetism or the electric, whatever it is. Electricians do this weird thing with their things, and that is correct. Now, there are some other ones, and if you want to memorize them all, that's fine, but I want to show you a little picture, which for some people is helpful. It's a little triangle, and at the corners you put I, J, and K. So how does this triangle work? Suppose you want to do I cross J, right? Start at I and go to J, and the answer is K. Suppose you want to do J cross I. Start at J, go to I, and then do you notice that you have to go against the arrow to K, and that makes it -K. So for instance, if I randomly said, what is K cross J? There's K, there's J, right? K cross J. What kind of I do you get if you do a K cross J? There's K.
Is it -I?
Yeah, if you go against the arrow, it's negative. if the arrow points in the right direction. It would be that. So there are a number of questions where they get you to do, what is that guy? Since there's probably only going to be two answers, plus or I, the guy that's not there, would you agree you could probably guess the answer half the time and you know it's the other one? And if you're really stuck, couldn't you do just a cross product with that? They also ask you to do something like this: I plus j cross I minus j. And this is essentially the algebra of cross products. It's actually the algebra of vectors as well. So I'll write it up here because I need more. So I'm going to do what the answer to that is without actually writing it in component form. Now, if I wanted to do this in component form, wouldn't this be 1, 1, 0 cross product with 1, negative 1, 0? Agreed? Let's see what that would look like. You FOIL it out. So you're going to get I cross I, take away minus I cross j, going this way, plus j cross I, and then the last one is minus j cross j. Would you agree that's kind of FOIL, right? Which may explain why they use that symbol. It's not really multiplying vectors together, but doesn't it have a lot of the similar algebra as multiplication has? Now, this guy here and this guy here are not the same. Do you notice that the order that the cross product is different? I'm going to change this guy here into the negative of I cross j. I decided to go that way. Are you comfortable with that answer? Okay. According to my little triangle, isn't I cross j k? And isn't that one k? So they combine to give me negative 2k. These two guys, they're special. Totally right out the blue. If you take a vector, any vector, including the vector I, and you do a cross product with itself. So in other words, this would be 1, 2, 3, and this would be 1, 2, 3, right? So if you did any vector, cross product with itself, what kind of vector do you think you might get out of that? Any vector.
Would it be a zero vector?
It would. So 0 vector, 0 vector. So the answer to this calculation was negative 2k. And I did it without doing it this way. I did it because I know how to FOIL. I know that these guys are the 0 vector, in which case they don't contribute to the answer. I know that these guys are really negatives of each other. And I also know that I cross j is a k. In fact, any two of them, don't you always get the third letter, right? So a j and a k will get you some kind of I, right? An I and a j will get you some kind of k, either a plus or a minus. So that was cross products that use I, j, and k's. Next thing we're going to look at is properties of cross products. We've actually touched on quite a few of them already. First property is, isn't A cross B orthogonal to A and to B? In fact, isn't that the way we created it? Done that one. Second property. A little bit different, but very similar to what we've already done. If A cross B is a zero vector, then A and B are parallel. So they don't need to be identical, but if they are, you get the zero vector. But if I do a vector, 2, 4, 6, and I do another vector, 20, 40, 60, right? They're parallel, different lengths, but they're parallel. Their cross product will always be zero. So actually, isn't that a way to test if two vectors are parallel? Is just find the cross product. And if the answer is zero, they're parallel. This one is to do with the magnitude of the cross product. And this is actually one of the ways you could use it, right? So the length of the cross product is the same number as the length of A times the length of B times the sine of the angle between them. Not as useful, right? But it is a property. Interesting property. That the magnitude of the cross product is just these two guys times the sine of the angle between them. And remember, the sine of the angle between them means that guy, right? Isn't that very, very similar to the dot product? What's the only difference?
Sine and cosine.
Yeah. Second difference, isn't this always going to be positive? And you might say, wait a minute, well, that's positive. I know that, that's a length, right? And that's positive, but that could be negative. Well, actually, no. If you find the sine of an angle theta, isn't the smallest it's going to be a 0, and isn't the biggest it's going to be 180? And all the other numbers, even the ones in the second quadrant, aren't they positive? So a dot product could be 0, a dot product could be positive, and a dot product could be negative. But a cross product is always going to be positive. So if you ever get a negative answer, look again, right? Something's not right. Now here's the fourth property, which is even weirder in my opinion, and I'm going to have to draw it. Imagine you've got your vector A, right? And you've got your other vector, your vector B. If you draw another vector parallel on this side, and you draw another vector parallel on this side, can you pretend that I drew a parallelogram there? Right. So this is A again, right? And this guy here is B again. The magnitude, whoops, the magnitude of the cross product is the area of that parallelogram. And there's no way in the world that that is intuitively why on earth that should be true. Why should the magnitude of the vector that's perpendicular to those two, why should the length of that vector be the area of this parallelogram? Would you agree that doesn't make sense? There's no reason it should be, but it is. So if you want to know the area of a parallelogram made up of a vector whose two sides are A and B, don't you find the cross product and then the magnitude, and that number is the area. Can you see why it has to be positive? Here's another property why we want to find them. There are lots of reasons why we want to find cross products, but here's another one. I'm going to basically just draw a quicker version of the same picture. There we go. The area of a triangle. So can you imagine that you built, you drew in 3-dimensional space two vectors, right, like that, wouldn't you be able to join the tips to make a triangle? Right, so there's the triangle I'm talking about. The area of this triangle is 1/2 the magnitude of the cross product. That one I can understand. If I accept that this is true, wouldn't you agree that that triangle is half a parallelogram? So the area of that triangle should be half that answer, right? So if I can accept that's true, then this comes from it. You think you're finished? One more property. This time you need three vectors, A, B, and C. And I'm going to pick my A going this way. I'm going to pick my B going this way. And I'm going to pick my C going this way. These are not orthogonal. If they look right angled, it's a coincidence of drawing, right? These three vectors are any three vectors, right? They're just not the same, right? They're different directions. If you take this shape and you add in some guys that are all parallel to it, and you join it together, can you imagine a box shape being created by the vectors A, B, and C? Can you imagine that box shape happening using A, B, and C? Now, my box looks very rectangular. Can you pretend it's more like a parallelogram? Because that's what it typically would be. Right? That shape is essentially the equivalent of a parallelogram in 3D. Does that make sense what I'm trying to draw? A parallelogram in 3D. Now, is that not a cool name? It's called a parallelepiped. One of the dwarfs or an elf in Lord of the Rings should have been called that. Isn't that a name that sounds like it should be an elf or a dwarf or something from Middle Earth? Right, here's my friend parallelepiped, right? I just like saying that word. Yeah.
Maybe that was Pippin's name and we just never used his full name.
Oh,
Maybe Pippin was
that's
a
it. They
nickname.
shortened it. It was a nickname. Yeah. Yeah, but he calls himself Pippin, right? That works. Now, you might, hopefully you will be pleasantly surprised that you can find the volume of a parallelepiped. And it's going to use a cross product, which again is amazing. I mean, it's pretty amazing it gives you a parallelogram. It's even more amazing it gives you this. What you might be surprised about is that the formula looks like this. It's a dot product, A, with the cross product B and C, and then you find the magnitude of it. Now, isn't A dot B cross C already a number, right? Because if you cover that up, isn't B cross C just a vector? And isn't E dot a vector a number, right? That's a dot product gives you numbers. So you might say, why do you need that absolute value around it? Don't some dot products give you -2? And we know it's a volume, right? So we want to make sure that it's positive. So we make an absolute value around it. Now, if you want to forget about the absolute value, that's fine. But when the answer -10 appears, well, you turn it into 10 on the next line because it is a volume. So that looks like I'm talking about the magnitude of a vector because we use the exact same symbols. But this symbol actually just means it's a positive number. And you might say, well, why did A go first? In fact, looking at that picture, shouldn't C go first? Well, here's an even more interesting property, that any combination of A, B, and C get you the same answer, the volume of that guy. So you could do C dot A cross B, and it would work. Couldn't you also do B dot A cross C, and it would work? And we even have a name for a calculation that's made up of 3 vectors, where you do a combination of dot and cross product, and it's called a triple product. So if you ever see the name triple product, you know there's 3 vectors involved and they're doing this. And because of what I just said, does it really matter who you put first, second, or third? Not really. What's the difference? Sometimes the combination gets you +4, sometimes it gets you -4, right? That's the only difference, right? You'll get the same value. So I want to do a question where we find a parallelogram and a triangle. And then I want to do one where we find a parallelepiped. Oh, that is a cool name. Every time I say it, I still think that's a cool name. Right. So let's suppose we have 2 vectors, A, 1, 3, 1, and vector B, and it's 2, 0, -1. And I want to find the area of the parallelogram where the 2 sides are described by these vectors, right? So pretend that's A in 3D, pretend that's B. So I'll find the cross product. We go I, we go J, we go K. This guy goes first. This guy goes second. So many I's, taking me so many J's, plus so many K's. Little thing set up. Here we go. To get the I's in, you cover up column I, you got -3, take away nothing, which is -3. Do the middle one now. You get -1, take away 2, which is what, -3. And then the last one is 0. Take away this guy, so you get -6. And the cross product is -3 plus 3, -6. Does that look good? Okay, so the area of the parallelogram is the magnitude of this vector. So these 2 lines do mean the magnitude, right? Because that's a vector. And that ends up being -3 squared plus 3 squared plus -6 squared. That's a 9 plus a 9 plus a 36. 18, 40, 54, that looks like. 54 can be thought of as 9 times 6, can't it? So this one would simplify as 3√6. So the area of a parallelogram that has its 2 sides, the vector A and B, the area of that parallelogram will be 3√6. And that might be question A. And question B is, what is the area of the triangle instead, right? So what's that guy? Well, isn't the answer to the area of the triangle just a half of that? Parallelogram, 3√6. The triangle, half of that. Are we comfortable with the application of why you might want to find a cross product to find areas of parallelograms or triangles in 3D space? Can you imagine how difficult that would be without cross products? Right? I'm not even sure where you would start. Well, let's find a volume of our parallelepiped then. A is going to be 1, 2, 3. B is going to be 0, 2, 1. And C is going to be 5, -1, 1. Now we want to find the volume of this shape. It's going to be A dot B cross C. Now, since any combination works and isn't cross products harder to do than dot products, wouldn't you want to pick two vectors that at least had zeros in them, because don't zeros make the calculations nicer, right? Because things disappear. Now, in this particular case, since there's only one that's a zero, this works really well, right? Can you imagine that this was called A and that was called B? I would probably switch places so that the one with the zero. The best world would be if this had zeros and this had zeros. Wouldn't you want to use them together? Because that would give you a very simple cross product. Or you can just take them as they come, and that works too. So I'm going to have to find this guy separately. This bit's here. After a while of doing these, it does become very mechanical. And you end up writing the darn thing down without thinking. Okay. 2 take away -1. 0 take away 5. 0 take away 10. And so this ends up being 3 +5 -10. And the volume is going to be the dot product that I've just written down. In this case, 1, 2, 3, dot product with 3, 5, -10. And dot product, 1 times 3, add 2 times 5, add 3 times -10. All good. I'm kind of happy this happened. Did you see in this case, my calculation ended up being a negative number? Right. I'm now about to fix it. The answer is 17. Right, we mentioned that 10 minutes ago, didn't we? The triple product, which is what we call this calculation, right, can sometimes be a negative number. And if that happens, you know that it's a positive. So if I'd kept this, wouldn't I have written that down? Or I would have done it without it, and then I would have written down 17 anyway, right? Because I know it has to be positive. So let's give you some puzzles and see if you can tell me geometrically, what does that mean, or how would this happen? The cross product A and B is 0. How could that happen? We've spoke about this before. Two vectors, A and B, have a cross product that ends up being the 0 vector. What do we call?
They're identical.
Identical does work, but in more general than identical, what else?
And parallel.
Agreed? Identical is just an example of parallel, right? So that is one way of taking. Well, I'm making an assumption here. I think it's an easy one to make. Would you agree that A and B better not be the 0 vector, right? Because that makes everything 0, right? So we're assuming that none of the vectors are 0 in any of the ones. This one, you deserve brownie points. How can a triple product be 0? Because it can happen. I'm going to draw 2 of the vectors. And can you imagine that when you draw 2 vectors, don't they lie in a piece of paper, right? Maybe an angled piece of paper. But any two vectors, right, in 3D space, isn't there a piece of paper that they could lie on, right? It's called a plane. What, and this is to help you, what is A dot B cross C equals 0 telling you about the vector A then?
It
Does
has
it
a
mean that they're
volume of
both-
0.
Say that again, Eric.
It has a volume of 0.
That's what the volume of the parallelepiped is correct. And how does that tell you what A is like?
It's going to
Yes.
be on the same plane.
That's the key, yeah. It has to be on the same plane. Because isn't the volume of a flat piece of paper 0? That makes sense. So if you want to test are two vectors parallel, can't you find their cross product? And if they're 0, they're parallel. And if it's not the 0 vector, they're not parallel. If you want to find if three vectors are on the same plane, and let me introduce the fancy name for that. It's called coplanar. If three vectors are on the same plane and you want to prove that they're on the same plane, don't you find the triple product? And if it's the number 0, remember this is a number and that's a vector, right? If it's the number 0, you've now proved that they are coplanar. That's kind of interesting. Because if you think of how could you prove that any other way? Right? If I just randomly gave you three vectors and says, are these three vectors coplanar? In other words, they all fit on the same piece of paper, right? Well, maybe they do and maybe they don't, right? Right now they don't. Can you agree they don't, right? And right now they do, right? I don't know how well they are orientated there. If I orientate it there, I'll have to go on. There we go. You can see they're coplanar, right? How would you do it? That's how you do it. But if you didn't know that, how would you do it, right? That would be a puzzle, wouldn't it? I mean, I'm not even, again, I'm not sure how you would tackle it. So to finish with today, the cross product is not going to be on this week's homework. Your homework's going to be extended to Monday, and your online test 7 will contain everything up to dot product, but not the cross product. I will keep the cross product live, just so you can get a head start on your homework for next week. We don't see you until Tuesday of next week, so it's going to be a much shorter week as well. So I figure out it's probably better to balance the homework a little bit that way. But feel free to do as many as you can with that. And what else? Oh, to finish with, I'm going to write down certain calculations, some of which can happen, and some of them are just not feasible. What's the other combination? Oh, I could do this one. Right, just a couple of random combinations of crosses, cross products and dot products. Do you think it's possible to do A cross B cross C? Is that a doable thing? Great.
Yes.
Right? Because isn't that going to get you a vector, and a vector cross vector is allowed? So, yep. Could you do A cross B dot C? No, that's a vector. That's a scalar, right? When I use the word scalar, I just mean it's a number like 40, right? Vector cross number ain't going to happen. What about A dot B dot C? You're shaking your head, Kira. Why? You're right. Why?
Because a dot is different than a multiple, so you can't do a vector dot a scalar. You'd have to do, if it was A times B dot C, you'd be fine. But
Okay. So a scalar dot a scalar ain't gonna happen. What about this one? A cross B dot B cross A. I know the answer to that. Oh, I don't know the answer to that. I'll take that back. I know the answer to this one, which is also possible. Why do I know? First, this is doable, right? You could calculate this, right? It's allowed. But why do I know the answer is 0?
Because the resulting would be parallel to each other.
Yes. And here's a property, if be our kind of last one. What happens if you do them in the other order? Right? So you do A cross B, you get a vector. What happens if you put that one second and this one third, right? You switch the order. Do you notice that the only difference is that one is positive and the other is negative? Right? One, your thumb points up the way, and the other, your thumb points down the way, right? But they are parallel, right? They just point different ways. Quite interesting property, that as well. But that is us, last name, and bye-bye, and I will hang out.